Hello, one and all, and welcome to Acid Basics, identifying acids and bases. What we're going to do is take a look at general motifs that we can use to predict if something is likely to act as an acid or a base in aqueous solution. Now, there's a countless number of acids and bases out there, and different chemical species behave differently depending on the environment that they're in. Accordingly, trying to memorize a list of acids and bases is just really not feasible. It's not practical. But recognizing certain motifs is, and that's what we're going to seek to do. So first, let's talk about identifying acids. Acids are colloquially written with a leading H oftentimes. While we're at it and talking about this motif, let's look at the 7 strong acids in aqueous solution. And I say 7 traditional strong acids because there are other strong acids out there, especially in the world of organic chemistry. But in terms of aqueous solutions, these are the most prevalent. There are the 3 diatomic ones. There's hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, the friendliest of them all, high. There's sulfuric acid, H2SO4, nitric acid, HNO3, chloric acid, HClO3, and perchloric acid, HClO4. These all dissociate completely. And notice that traditionally these are written with a leading H. Not always, but just oftentimes to emphasize that they can lose that proton. Now, some other examples of acids. We've got hydrofluoric acid, HF, carbonic acid, H2CO3. We've got hydroazoic acid, HN3. We've got phosphoric acid, H3PO4, and then citric acid, H3C6, H5O7. These are just some examples of hundreds of thousands of different types of acids out there. And these are just some examples of weak acids that we just listed. Carboxylic acids, arguably the most important functional group in terms of acid chemistry. And remember, a carboxylic acid is a COOH. So 2 examples, we've got acetic acid, CH3COOH, and its structure looks like this. Oh, there we go. There we have our carboxylic acid motif. Another example is benzoic acid. And here's an image of benzoic acid. They both have that functional group, and that functional group is good at polarizing the OH bond to remove the hydrogen. Plus, once the hydrogen's removed, there's resonance in the conjugate base, which helps stabilize them. Anything that has an acid dissociation constant, Ka, can act as an acid. So a Ka reaction, for example, the Ka of hydroazoic acid, HN3, is 1.9 times 10 to the negative 5th. How do we write this reaction? Well, all you have to do is take your acid, in this case, HN3, and then we're going to make it an equilibrium process because this is a weak acid. It's going to turn to H+, classic, and the conjugate base, in this case, N3-. Ka reactions are always just taking your acid and plucking off an H+. That's all there is to writing a Ka reaction. Now then, oxides. Oxides are neutral compounds containing 2 elements, oxygen and something else. The trend for oxides is nice and straightforward. So summon the periodic table, or at least a cartoon of the periodic table. Generally speaking, metal oxides are basic, non-metal oxides are acidic, metalloid oxides are amphoteric, and there are some transition metal oxides that are also amphoteric. In general, though, the character of the oxide, as you go up and to the right on the periodic table, it becomes more and more acidic. So let's use this, talk about oxides, to segue into identifying bases. We said that metal oxides are generally speaking basic, and that leads us to the fact that most metal hydroxides, most things containing a metal and OH, are basic. And let's look at the traditional strong bases. They are group 1 metal hydroxides, which include LiOH, NaOH, KOH, RbOH, CSOH, and FrOH. And group 2 metal hydroxides, with a little caveat here, calcium and below. So the larger group 2 metal ions and 2 hydroxides. So calcium hydroxide, strontium hydroxide, barium hydroxide, technically radium hydroxide, etc. These are all metal hydroxides. They can be made from metal oxides, and these are all strong bases that will dissociate completely in aqueous solution. Ammonia and amines. We said before that carboxylic acids are arguably the most important functional group in terms of acid chemistry. Well, amines are arguably the most important in terms of basic chemistry. Amines are organic molecules that contain a nitrogen with a lone pair, and that lone pair is good at donating itself, so they act as good Lewis bases. So here's some examples. First, ammonia, NH3. Classic. Look at that lone pair of electrons just waiting to be donated. Another one, how about methylamine, CH3 and H2. There we just have a methyl group, a CH3, with an amine. Cool. And then finally, trimethylamine, which is three, CH3 groups coming off of the nitrogen with its lone pair that it can use to donate. As with acids having their Ka, the acid dissociation constant, weak bases have something called a base hydrolysis constant. So if any molecule or chemical species has a Kb, that means it can act as a base. And the reaction is again very straightforward. So for example, the Kb of, and this is pyridine, is 1.7 times 10 to the negative ninth. How do we go about writing a reaction? It's always gonna be the same thing. You take your weak base, in this case pyridine, C5H5N, and for a Kb reaction, you always react it with water. So plus H2O liquid, because with weak bases, it turns out that water is the source of the hydroxide. So be an equilibrium process, our base is going to accept a proton to become the conjugate acid, and the water then, since it lost its H plus, just becomes OH minus. And there we have our classic Kb reaction. And again, anything that has a Kb can act as a base. Conjugates. The conjugate of a weak acid is a weak base. So for example, here we have hypochlorous acid, HClO. When it dissociates, it's an equilibrium process to turn into H plus and ClO minus. Now, this is a two-way street. The H plus and that ClO minus can get back together again and form HClO. It's not like strong acids, which dissociate completely. So that means that ClO minus, aka hypochlorite, can act as a base. And how it would do that? Well, classic base hydrolysis. We would react it with water. It's going to pull an H plus out of water to make HClO and leave behind hydroxide. So the conjugate of a weak acid is a weak base. Likewise, the conjugate of a weak base is a weak acid. Okay, so the conjugate of a weak thing is a weak thing. The conjugate of a polyprotic weak acid can act as a base, but if it has more protons to give up, it can also act as an acid. So we would call that amphoteric. And a classic example is carbonic acid, H2CO3. It can lose a proton, so give up H plus and become bicarbonate, HCO3 minus. Losing the first proton, we give a very specific Ka2, we call it Ka1, because appropriately enough, it's the first proton being let go. Now, HCO3 minus can accept a proton, so it can act as a base. And if we want to have it act as a weak base in aqueous solution, it can accept that proton from water. So our classic Kb reaction, HCO3 minus plus water yields H2CO3 and hydroxide. So that's it acting as a base in aqueous solution, but also it could instead lose its other proton. So we could take HCO3 minus, we could have it lose an H plus, and that would leave carbonate behind, CO3 2 minus. If it's the second proton being lost, we call that Ka2. If it's the third proton being lost, we call it Ka3, et cetera, et cetera, et cetera. Now this one only has two Kas because there's only two protons to lose. Now, a big difference between weak acids and strong acids, well, I mean, the fundamental difference is the extent to which they dissociate. The conjugate of a strong acid is a negligible base. And we can see that if we consider what type of arrow a strong acid uses. So take, for example, hydrochloric acid, HCl. When it goes all out. It dissociates into H plus and Cl minus. This is a one-way street. H plus and Cl minus, they are never getting back together, okay? They are splitsky, they are done with each other. And think about it. If H plus and Cl minus can't get back together to form HCl, so this is a no-go, I'm gonna put an X through that. if they can't get back together to form HCl, do you think that there's any way that Cl minus is going to be able to rip an H plus off of water and break a covalent bond in the process? Do you think that Cl minus, if it can't accept an H plus to begin with, is going to be able to break a bond in water to accept an H plus to become HCl and OH minus? The answer is a resounding no. No. No, it cannot. So let's X this one out as well. So that's why the conjugate of a weak acid is a weak base. The conjugate of a strong acid is a negligible base. And as long as you remember that relationship, you're good to go. Conjugate of a strong thing is negligible. The conjugate of a weak thing is a weak thing. And that will always hold up true. And then finally, we're going to look at ions and salts. Cations tend to be acidic. And when you think about what acids do, this makes sense because positive charges are better at accepting electrons. Remember, the Lewis acid definition is that acids accept electrons. So if something is positively charged, it's going to be more attracted to electrons. Additionally, if you have positively charged molecules that contain hydrogens in them, they're going to be more likely to be able to get rid of that H plus. Now, on the other hand, when you think of the Lewis base definition, a Lewis base is something that donates electron density. Accordingly, anions tend to be basic. Negative charges are better at donating electron density, which makes sense because if they're negatively charged, they've got electron density on them. Additionally, if they're negatively charged, there's more of a chance that they're going to accept H plus because opposites attract. H plus, negative charge, more of an attraction. Now, there are exceptions to this rule in aqueous solution, but the exceptions are really straightforward if you think about strong acids and strong bases and how their conjugates are negligible. So let's do the anions that are not basic in aqueous solution. In aqueous solution, any anion can act as a base and hydrolyze water except for, and I think you'll see a pattern here, Cl minus, Br minus, I minus, ClO4 minus, ClO3 minus, NO3 minus, and HSO4 minus. Now, wait a minute. These look awfully familiar. These are the conjugate bases of strong acids. Okay? Remember, it's a one-way street. Those conjugate bases cannot accept a proton. So these 7 anions are not going to be able to hydrolyze water. They're far too weak. In fact, water itself hydrolyzes itself more appreciably than these things would. Okay, so generally speaking, anything else with a negative charge that's not the conjugate base of a strong acid can act as a base in aqueous solution. So other examples, ClO minus, hypochlorite, that can act as a base. Carbonate, CO3 minus, can act as a base. NO2 minus, nitrite, can act as a base. F minus can act as a base. These are not the conjugates of strong acids, et cetera, et cetera, et cetera. Additionally, in aqueous solution, any cation can act as an acid and donate or create H plus, except for, and again, I hope you'll see a pattern here, Li plus, Na plus, K plus, Rb plus, Cs plus, Fr plus, Ca2 plus, Sr2 plus, Ba2 plus, and Ra2 plus. Now, do these look familiar? I hope so, because these are the metal cations that are related to strong bases. These are the group 1 metal cations and the group 2 metal cations, calcium and below. Generally speaking, anything else with a positive charge is going to be able to act as an acid in aqueous solution. Finally, let's look at salts. Let's apply what we just talked about to decide if each of these salts is acidic, basic, or neutral. Generally speaking, what we're going to do to figure out if a salt is acidic, basic, or neutral is split it into its constituent ions. And then ask ourselves, is the cation acidic? Is the anion basic? And let's do 3 different examples, which, spoiler alert, one of them is acidic, one of them is basic, and one of them is neutral. The first one is sodium hypochlorite. This is also known as bleach. Let's first break it into its constituent ions. So the metal is going to be the positively charged cation, Na+, and then the non-metal stuff is going to be negatively charged ClO-. Na+, well, that's a group 1 metal cation. Sodium hydroxide, NaOH, is a strong base. That makes this one neutral. This is a negligible acid. ClO minus, however, has a negative charge, and it's not the conjugate of a strong acid. Therefore, it is basic. Now let's do the same thing. This next one is an example of an ammonium salt. Whenever you have a nitrogen that has 4 bonds on it, you're going to have a positive formal charge around that functional group, and it's going to dissociate readily in aqueous solution. So this will dissociate into NH4 plus, aka ammonium, and Cl minus. NH4 plus, it has a positive charge, but it's not a group 1 metal cation or a group 2 calcium and below. This is going to be acidic. Turns out ammonium is pretty good at getting rid of it in H plus. Cl minus is the what of a what, therefore making it what? Well, it's the conjugate base of a strong acid, therefore making it negligible. So this is a neutral ion in aqueous solution. Then the final example is lithium perchlorate. It'll associate into Li plus, and perchlorate, ClO4 minus. Li plus is a group 1 metal cation. It's neutral. ClO4 minus is the what of a what, therefore making it what? That's right, it's the conjugate base of a strong acid, therefore making it negligible. And that wraps up the general motifs for identifying acids and bases. Hope that you found this useful. Thank you for watching and have a wonderful rest of the day.